Hi guys, so welcome back to the channel and welcome back to Excel Island, where the goal and objective is to learn and master Python over the next 100 days. So we are on our seventh course, which is Introduction to Statistics in Python. So we're actually learning about how to perform statistical analysis in the Python environment. So we've started this learning journey over a couple of live streams. So today is day 52. We started over 50 days ago. So the goal is 100 days of learning. So we have 9 courses to complete in the career track, data analysis with Python on the DataCamp platform. So if you are new to the channel, that is what we've been doing so far. So if you're looking to catch up from day one all the way till day 51, that was the last live stream, you can go to the live stream tab on Excel Island YouTube channel. You are going to see all of that on the channel. So without any further introduction, let's continue for where we stopped on day 51. So we're actually looking at completing the last chapter of the course of the Introduction to Statistics, which is chapter 4 on today's live stream. So I'll just start sharing my screen real quick. So all the data set exercise files that we've been using so far is linked under the YouTube description. So to make sure to follow those links and have access to all the files. So these are the files we've used in this chapter 4 in this chapter 4 or in this introduction in statistics, which is the seventh course learning journey. So all other data sets is also linked under the YouTube description. So just follow the link and have access so you can practice and build your simple statistical analysis like this. So let's continue. So we can see we're on the last chapter, which is chapter 4. So we've covered summary statistics in Python, random numbers and probability, where we actually looked at different probability type or different distributions type. So we look at discrete distribution, continuous distribution. So the next chapter was on random numbers, mode distribution, and the central limit theorem. So on this now, we're actually looking at correlation and experimental design. So I'll just continue. So hopefully we can just complete this last lesson today, or we finish it in the next live stream. So let's see what we can do today. So I have my my file, Jupyter notebook launched already. This was where we stopped on the last lesson, where we actually calculated correlation of two different variables from this data set, life expectancy, and so we focused on only these two columns. We actually calculated how correlated are or are these two variables actually correlated. And we calculated the correlation score. You can see it is 78%. It has a 78% correlation score. So the world happiness and life expectancy, or the life expectancy column and the happiness score, which is just giving us information about the life expectancy and happiness score of different population in each country. So let's continue.
While correlation is a useful way to quantify relationships, there are some caveats. Consider this data. There is clearly a relationship between x and y, but when we calculate the correlation, we get 0.18. This is because the relationship between the two variables is a quadratic relationship, not a linear one. The correlation coefficient measures the strength of linear relationships, and linear relationships only. Just like any summary statistic, correlation shouldn't be used blindly, and you should always visualize your data when possible. Let's return to the mammal sleep data. Here's a scatter plot of each mammal's body weight versus the time they spend awake each day. The relationship between these variables is definitely not a linear one. The correlation between body weight and awake time is only about 0.3, which is a weak linear relationship. If we take a closer look at the distribution for body weight, it's highly skewed. There are lots of lower weights and a few weights that are much higher than the rest. When data is highly skewed like this, we can apply a log transformation. We'll create a new column called log body weight, which holds the log of each body weight. We can do this using np.log. If we plot the log of body weight versus awake time, the relationship looks much more linear than the one between regular body weight and awake time. The correlation between the log of body weight and awake time is about 0.57, which is much higher than the 0.3 we had before. In addition to the log transformation, there are lots of other transformations that can be used to make a relationship more linear, like taking the square root or reciprocal of a variable. The choice of transformation will depend on the data and how skewed it is. These can be applied in different combinations to x and y. For example, you could apply a log transformation to both x and y, or a square root transformation to x and a reciprocal transformation to y. So why use a transformation? Certain statistical methods rely on variables having a linear relationship, like calculating a correlation coefficient. Linear regression is another statistical technique that requires variables to be related in a linear manner, which you can learn all about in this course. Let's talk about one more important caveat of correlation that you may have heard about before. Correlation does not imply causation. This means that if x and y are correlated, x doesn't necessarily cause y. For example, here's a scatter plot of the per capita margarine consumption in the US each year versus the divorce rate in the state of Maine. The correlation between these two variables is 0.99, which is nearly perfect. However, this doesn't mean that consuming more margarine will cause more divorces. This kind of correlation is often called a spurious correlation. A phenomenon called confounding can lead to spurious correlations. Let's say we want to know if drinking coffee causes lung cancer. Looking at the data, we find that coffee drinking and lung cancer are correlated, which may lead us to think that drinking more coffee will give you lung cancer. However, there's a third hidden variable at play, which is smoking. Smoking is known to be associated with coffee consumption. It is also known that smoking causes lung cancer. In reality, it turns out that coffee does not cause lung cancer and is only associated with it, but it appeared causal due to the third variable, smoking. This third variable is called a confounder or lurking variable. This means that the relationship of interest between coffee and lung cancer is a spurious correlation. Another example of this is the relationship between holidays and retail sales. While it might be that people buy more around the holidays as a way of celebrating, it's hard to tell how much of the increased sales is due to holidays and how much is due to the special deals and promotions that often run around the holidays. Here, special deals confound the relationship between holidays and sales. Now that you've learned how to use correlation responsibly, time to practice.
Oh, that's good. So what we learned is that correlation does not equate causation. Because two things are highly correlated doesn't mean one causes the other to occur. That's one of those simple correlation techniques you have to know. Let's discuss what can't correlation measure. So why the correlation coefficient is a convenient way to quantify the strength of a relationship between two variables. It's far from perfect. In this exercise, you will explore one of the caveats of the correlation coefficient by examining the relationship between a country's GDP per capita and happiness score. So we have access to the data sets already, which is a country's GDP per capita, which is this information here, and the happiness score. Are they actually correlated? So we need to figure that out. So pandas as PD, matplotlib as pyplots, matplotlib.pyplot as plt, and cbon as cns are imported, and word happiness is loaded. Let me just launch all of these again. So we've covered how to use most of these libraries. So you can just catch up from day one all the way till today. So you can understand what all these libraries are doing. I'm just running that line of code again. Okay. It says create a C-bond scatter plot without a trend line, showing the relationship between GDP per cap on the x-axis and life expectancy on the y-axis. Okay, so we've created something like that before. This has a trend line. This doesn't have a trend line. So to create a what? A seaborne scatter plot. I'll just copy this. So now I want to make GDP per capita to be on the x-axis and life expectancy to be on the y-axis. If I call on plot.show, it's going to show me the plots. Let's run the code and see. Voila. Hmm. They're actually correlated. But let me see. Let's see it in action. Let me just copy this line of code here. Make use of it. It says without a trend line. So there's no trend line there. If I want to show a trend line, I have to update the code. Let's see it here. Voila. So you can see our life expectancy here and our GDP. So we're only taking these two columns, GDP per capita and life expectancy information from here. As you can see, GDP, life expectancy. Let's submit that. Good, we got that. So calculate the correlation between GDP per capita and life expectancy and store as core. So to calculate the correlation, we just use this line of code here. Or so this will now be GDP per capita GDP per cap and life expectancy will be on the y-axis there. Let's run the code. You can see there's 70% correlation between GDP per capita and life expectancy. So if you now try to run this code, let's see. Let's see, we get 70% correlation coefficient there. Now, the correlation between GDP per capita and life expectancy is 0.7. Why is correlation not the best way to measure the relationship between these two variables? Hmm. Correlation measures how one variable affects another. Correlation only measures linear relationship. Correlation cannot properly measure relationship between two numerical variables. Oh, is that true? Let's see. So you could say the GDP per capita of the country does not necessarily equate that the people in the country are happy, because it doesn't mean that one is happening and the other one is happening interchangeably. So that's one of the reasons. But let's see the best option here to choose. That is correct. Mm. That's correct. So the coefficient cannot account for any relationship that aren't linear, regardless of the strengths. So you can see, so correlation only measures linear relationship. And this is non-linear. That's it. They are kind of packed at the upper part of the graph. So correlation actually measures relationship between two numerical variables. And correlation measures how one variable affects the other one. So that's the best answer. Transforming variables. When variables have skew distribution, just like we have here, I think there's a skew distribution in this instance here. I see they are kind of actually packed to the higher life expectancy, which doesn't necessarily mean that because the higher the GDP per capita of the country, the longer the life expectancy of the residents. Let's see. When variables have skew distributions, they often require a transformation in order to form a linear relationship with another variable so that correlation can be computed. In this exercise, you perform a transformation yourself. Pandas as PD, we have all that already. So create a scatter plot of happiness score versus GDP per capita and calculate the correlation between them. We've done that already. Let's see. So create a scatter plot of happiness. Okay. This time around is happiness versus GDP per capita. Okay. Then GDP per capita. Okay. You can just say PLT dot show there. They want to calculate the correlation between them, which is the score. So my core would now be happiness GDP per capita. Okay. Let's see. Let's run the code here first. You can see. So this is the scatter plot showing the happiness score versus GDP per capita. This is kind of linear. Yes, this is quite linear. And the correlation between them is 0.7. Let me just uh, cut this line of code and show it in another line, which is much more better. Let's run the code because we have same result here. Same results. Ooh, we didn't get that. Because question is supposed to confess. Okay. I think we are supposed to have GDP per capita on the axis. Let's see. Okay. This has to be on the x-axis. Why this should be on the y-axis. Let's run the code again. Voila. Now we have something entirely different. Interesting. Now let's see. Voila. I'm seeing something different here. Uh-oh. Let's calculate the correlation, which is 79%, 72%. So we have seen, why am I seeing something different here? My graph is kind of showing something entirely different here. Why is it showing me something different also? Let's submit and see. Ooh, we got that. It's similar. You can see. Yeah, it's quite similar. So add a new column to what happiness called log GDP per capita. Okay. It says add a new column to what happiness called log GDP per cap that contains the log of GDP per cap. Okay. What happiness log GDP per cap equals to np.log np.log open brackets. That's going to be what happiness. I'll just copy this part of the code. It's going to be like that. It now says create a Seaborn scatter plot of happiness and log. So I'm going to create a Seaborn scatter plot for the world happiness and the log GDP we just calculated. We just convert. So I'm going to convert this data point to something else. And this is going to change to log GDP. Let's see. Let's copy that. And now see we should calculate the correlation. Now calculate the correlation between these two variables. These two new variables. Let's see. So it's going to be log GDP per cap. Okay. Hope that's clear a little bit. Let's run the code and see. Ooh, we definitely made a mistake in this in our log GDP per cap. Let's see. I made a mistake somewhere. Oh, my mistake was referring to, hold up a minute. My log GDP per cap. I was supposed to be referring to the GDP per cap for the information. Sorry about that. Aha. Now we have a better view. Since I want to convert my GDP per cap to log, I just use np.log for that. Let's pick this line of code and give it a better shot in this interface here. So the first thing to do is to create a log GDP per cap for that information. Hold up a minute, 1 second there. So the first instruction to convert that our GDP per cap to a better variable that would be that would be easy to visualize. So we've done that already. So we did that by converting. So let me do that in this interface. So create a log per cap column. So let me just copy this instruction here. If you're keeping records, I can easily track, know what that line of code is doing. Let me cut this out. If I run this line of code, we shouldn't have any error. Next is to now create a scatter plot using the information, the new log that we created. You can see that's the same happiness score and log GDP per cap, quite different from what we are visualizing here. This is much more better. Then we just run the correlation to know what the actual correlation is, which is 80% compared to the showing 72%, and it's not linear. So this is more linear. You can see that was the essence of that. Terrific transforming. So the relationship between GDP per capita and happiness became more linear by applying a log transformation. So log transformations are great to use on variables with a skewed distribution such as, as GDP. So that was the essence of that. Let's continue. Oh, ignore this. I've just been learning over a couple of 100 days now. Just picking up some new knowledge. So does sugar improve happiness? So a new column has been added to word happiness called grams sugar per day. So we want to see if the consumption of sugar actually improve the happiness of people in each country. So are they actually correlated? If you consume more sugar, will you be happy or will you be sad? It's just as simple, basic analogy like that. So it contains the average amount of sugar eaten per person per day in each country. So in this exercise, you examine the effect of a country's average sugar consumption on its happiness score. So pandas as PLD, so we've imported all the important libraries. So we need to create a seaborne scatter plot showing the relationship between gram sugar per day on the x-axis and happiness score on the y-axis. So sadly enough, I don't have that column in my own data set here. Grams per sugar per day. Let me see, do I have that? No, I don't have that in my own data set here. I'm not going to perform this analysis on this interface alone. So let me just copy this line of code and make use of it again. Just to make things faster. So we need to show the grams per sugar per day on the x-axis. and happiness score on the y-axis, which is that. Then we need to create a correlation, the correlation coefficient for that, which is quite straightforward. So we spent 30 minutes on the live stream. So this is going to change to grams sugar per day. So if you run the code, let's see, this is taking a little bit of time. Voila. This is 0.69, which is quite strong. Probably it is the correlation, the correlation between the two variables is quite strong. Let's see. So question, based on this data, which statement about sugar consumption and happiness scores is true? You can see they are kind of dispersed all over the places. So increased sugar consumption leads to a high happiness score. You can see the sugar consumption per day. So the more sugar consumption, can see that as the number of sugars increase, consumption increase, the happiness score kind of goes up again because we have more data points here. Probably it increased, but let's see. Lower sugar consumption results in lower happiness score. Can also say there are more this lower sugar consumption here. The happiness score of these people here is kind of low. Increased sugar consumption is associated with higher happiness score, or sugar consumption is not related to happiness. Hmm. Sugar consumption, the higher it goes, you can see. So the higher the sugar consumption, the higher the happiness score goes up. So you can actually see that on the graph itself. It's a nice interpretation of correlation. If correlation always implied that one thing causes another, people may do some nonsensical things like eat more sugar to be happier. That's true. But you know sugar is not good for the body, it causes diabetes. You probably don't want to consume more sugar to be happy. Probably you definitely want to exercise more, eat healthy, and eat more fruit and vegetables. But just ignore the data points. So this is just probably a fictional data points. It shows a study. So let's see what we have here. Okay, co-founders. So a study is investigating the relationship between neighborhood residents and lung capacity. Researchers measured the lung capacity of 30 people from neighborhood A, which is located near a highway, and 30 people from neighborhood B, which is not near a highway. Both groups have similar smoking habits and a similar gender breakdown. Which of the following could be a co-founder in the study? A co-founder. That would be a smoking status. Let's see. Oh, that's not true. Hmm. hmm. So neighborhood A is located near a highway, and 30 people from neighborhood B, which is not near a highway. Both groups have similar smoking habits and similar gender breakdown. We could go for gender breakdown or air pollution or lung capacity. Ah, okay, lung capacity is responsible to be studied. If you go for air pollution, correct, you expect there to be more air pollution in the neighborhoods situated near the highway, which can cause lower lung capacity. Interesting. Let's see what we need to cover. Designs of experiments. Can we cover this today? Let's design of experiments, study types, and look longitudinal versus cross-sectional studies. Let's see. Let's cover this today. It's quite straightforward.
Often, data is created as a result of a study that aims to answer a specific question. However, data needs to be analyzed and interpreted differently, depending on how the data was generated and how the study was designed. Experiments generally aim to answer a question of the form, what is the effect of the treatment on the response? In this setting, treatment refers to the explanatory or independent variable, and response refers to the response or dependent variable. For example, what is the effect of an advertisement on the number of products purchased? In this case, the treatment is an advertisement, and the response is the number of products purchased. In a controlled experiment, participants are randomly assigned to either the treatment group or the control group, where the treatment group receives the treatment and the control group does not. A great example of this is an A/B test. In our example, the treatment group will see an advertisement and the control group will not. Other than this difference, the groups should be comparable so that we can determine if seeing an advertisement causes people to buy more. If the groups aren't comparable, this could lead to confounding or bias. If the average age of participants in the treatment group is 25 and the average age of participants in the control group is 50, age could be a potential confounder if younger people are more likely to purchase more, and this will make the experiment biased towards the treatment. The gold standard or ideal experiment will eliminate as much bias as possible by using certain tools. The first tool to help eliminate bias in controlled experiments is to use a randomized control trial. In a randomized control trial, participants are randomly assigned to the treatment or control group, and their assignment isn't based on anything other than chance. Random assignment like this helps ensure that the groups are comparable. The second way is to use a placebo, which is something that resembles the treatment but has no effect. This way, participants don't know if they're in the treatment or control group. This ensures that the effect of the treatment is due to the treatment itself, not the idea of getting the treatment. This is common in clinical trials that test the effectiveness of a drug. The control group will still be given a pill, but it's a sugar pill that has minimal effects on the response. In a double-blind experiment, the person administering the treatment or running the experiment also doesn't know whether they're administering the actual treatment or the placebo. This protects against bias in the response as well as the analysis of the results. These different tools all boil down to the same principle. If there are fewer opportunities for bias to creep into your experiment, the more reliably you can conclude whether the treatment affects the response. The other kind of study we'll discuss is the observational study. In an observational study, participants are not randomly assigned to groups. Instead, participants assign themselves, usually based on pre-existing characteristics. This is useful for answering questions that aren't conducive to a controlled experiment. If you want to study the effect of smoking on cancer, you can't force people to start smoking. Similarly, if you want to study how past purchasing behavior affects whether someone will buy a product, you can't force people to have certain past purchasing behavior. Because assignment isn't random, there's no way to guarantee that the groups will be comparable in every aspect, so observational studies can't establish causation, only association. The effects of the treatment may be confounded by factors that got certain people into the control group and certain people into the treatment group. However, there are ways to control for confounders, which can help strengthen the reliability of conclusions about association. The final important distinction to make is between longitudinal and cross-sectional studies. In a longitudinal study, the same participants are followed over a period of time to examine the effect of treatment on the response. In a cross-sectional study, data is collected from a single snapshot in time. If you wanted to investigate the effect of age on height, a cross-sectional study would measure the heights of people of different ages and compare them. However, the results will be confounded by birth year and lifestyle, since it's possible that each generation is getting taller. In a longitudinal study, the same people would have their heights recorded at different points in their lives, so the confounding is eliminated. It's important to note that longitudinal studies are more expensive and take longer to perform, while cross-sectional studies are cheaper, faster, and more convenient. Time to practice your study design skills.
Ooh, very interesting. So there are different design skills or different design types. Okay, that is still loading. It says which controlled experiments are ideal. Many situations and research questions are not conducive to a controlled experiment. In a controlled experiment, causation can likely be inferred if the control and test groups have similar characteristics and don't have any systematic difference between them. On the other hand, causation cannot usually be inferred for observational studies, whose results are often misinterpreted as a result. So in this exercise, you will practice distinguishing controlled experiments from observational studies. Ooh, let's see. Purchasing rates are compared. It says purchasing rates are compared between users of an e-commerce site who are randomly directed to a new version of the home page or old version. Purchasing rates are compared. So they're randomly directed. Is it controlled experiment or observational? Since you're not forcing them, I'll go for observational for this. Since they're not assigned to different subjects are randomly assigned to a diet and weight loss. So a diet and weight loss is compared. This is controlled. Prevalence of heart disease is compared between veterans with PTSD and veterans without PTSD. So you have to know those veterans with PTSD and the veteran without PTSD. Let's go for controlled. Asthma symptoms are compared between children randomly assigned. You can say they were randomly assigned to receive professional home pest management service or PES. Okay, let's see. So a week ago, the home page of an e-commerce site was updated. Purchasing rates are compared between users who saw the old and new home page versions. Who saw the old. So they're kind of controlling this in this scenario here. Ooh, whoa, I misinterpreted it a lot. Are you telling purchasing rate are compared between users of an e-commerce? Randomly directed. Ooh. I messed it up. So if you're telling me asthma symptoms are compared between children randomly assigned to receive professional home pest management service or pest management education, but they could actually randomly assign them to either receive pest management service or pest management education. Purchasing rates are compared between users of an e-commerce site who are randomly directed to a new version of the home page. This observation is quite funny. Prevalence of heart disease is compared between veterans with PTSD and veterans without PTSD. Interesting. Marvelous matching. Now that you can distinguish between controlled experiments and observational studies, you'll be able to tell them you'll be able to tell when an observational study claims to establish a causal relationship. Okay, that's interesting. So we move on. We just have to understand what is observational experiments and controlled experiments. So controlled experiments, participants are assigned by researchers to either treatment group or control group. Treatment group see advertisement, control group does not. Okay. It says groups should be comparable so that causation can be inferred. If groups are not comparable, this could lead to confounding bias. Treatment of age group, control group, 50. Age is a potential co-founder. Okay. So can you just watch the difference between, okay, let's say longitudinal versus cross-sectional studies. A company manufactures thermometers and they want to study the relationship between a thermometer's age and its accuracy. To do this, they take a sample of 100 different thermometers of different ages and test how accurate they are. Is this data longitudinal or cross-sectional? Hmm. So for longitudinal study, participants are allowed over a period of time. So cross-sectional. mm, Can it be both? It can be both. So it is actually cross-sectional. So perfect. So this is a cross-sectional study since researchers aren't following the same set of thermometers over time and repeatedly measuring their accuracy at different ages. Okay, that's a lot of technical stuff to understand. Oh,
Congratulations on completing the course. You now have foundational statistics skills that you can use in your analyses and build upon further. In the first chapter of the course, you learned about what statistics can do, as well as summary statistics to measure the center and spread of a distribution. In the second chapter, you learned how to measure chance and how to use and interpret probability distributions. You also learned about the binomial distribution. In Chapter 3, you learned about the normal distribution and the central limit theorem, one of the most important ideas in statistics. You also saw how the Poisson distribution can be used to model countable outcomes. In the final chapter, you saw how to quantify relationships between two variables using correlation. You also learned about controlled experiments and observational studies, and the conclusions that can and cannot be drawn from them. There's still much more that you can do with statistics, and much more to learn. Your new skills will set you up for success in this course on the foundations of regression. Thanks for accompanying me on this statistical journey. Congratulations again.
voila. So our next course should be, so we've covered introduction to statistics in Python. If I go on that career track real quick, so we should start looking at the eighth course. Probably we have our next project next. We have a project to perform next. So we've covered introduction to statistics. So we have Seaborn, introduction to data visualization with Seaborn. Okay, so let's see. Right now, we are going to start that on day 53. We are going to visualize this history of Nobel Prize winners in data manipulation with pandas, importing and cleaning data with Python. We still have quite a lot to cover. All right, so that will be the end of the live stream for today. If you enjoyed this statistic learning journey with Python with me, do what to give this video a thumbs up, hit that subscribe button, and I'll see you on the next video on the channel on day 53 as we start data visualization in Python with Seaborn. Let's go. Let's get back to work and have a wonderful